So good morning students, this is Aravind, Assistant Professor, Department of Triplet, DBSIT KAVALI. So in the previous session, I am discussed about some voltage regulation, definition of voltage regulation, and next listing the voltage regulation methods of an alternator. And in that class only, I am discussed direct loading method and EMF method. And now I am going to discuss in this class, that is MMF method of an alternator. That is the second indirect method. Okay, so firstly we will see the diagrammatic representation of MMF method. So here the MMF method is used for determining the voltage regulation of an alternator or synchronous generator, is also called ampere turns method. So you already know this one. In the first class only I discussed these things. So this MMF method is also known as ampere turns method or Rother's MMF method. Okay, so this method is used for determining the voltage regulation of an alternator. So this MMF method is based on the results of open circuit test and short circuit test of an alternator. So in the previous method, that is in the EMF method also, we are conducted the open circuit and short circuit test. So here also I am going to perform open circuit test and short circuit test on an alternator. So here, for any synchronous generator or alternator, MMF is required. MMF is required. So which is a product of field current and turns of the field winding for two separate purposes. Okay, firstly, so it must have an MMF necessary to induce the rated terminal voltage on open circuit. Okay, and next it must have an MMF equal and opposite to that of the armature reaction MMF. Okay, so these are the two separate purposes we are using the MMF. Okay, so firstly, in the previous case also, in the previous method also, we are to taken some assumptions. That is, saturation effect is neglected and leakage reactance is considered as armature reaction reactance. So in this method, the drop due to leakage reactance is considered as armature reaction reactance. So in the previous case also, I discussed this one. Okay, in the EMF method also, I discussed these things. Okay, here, hence, entire drop is due to flux phenomenon. So in the previous method, I am taking the voltage phenomenon. So the entire drop is due to the voltage phenomenon. Hence, this method is known as EMF method in the EMF method. But here, entire drop is due to flux phenomenon. Hence, this method is known as MMF method. Okay. So this method requires mainly two characteristics of alternator. So they are open circuit characteristics, that is from the OC test, that is open circuit test, and secondly we have short circuit test, that is from the short circuit characteristics, short circuit characteristics from the short circuit test. Okay, next, so here the field MMF which is required for inducing the rated terminal voltage on the open circuit can be obtained from open circuit test results and open circuit characteristics. So this is denoted as F naught, F suffix 0, that is F naught. So synchronous impedance consists of two components. Okay, they are armature resistance and synchronous reactance. Okay, these are the two components for the synchronous impedance. So now synchronous impedance also has two components. So actually synchronous impedance consists of two components. One is armature resistance, that is Ra, and synchronous reactance, that is Xa. Okay, so here the synchronous reactance also has the two components. One is armature leakage reactance, that is XL, and armature reaction reactance, that is XA. Okay, so in the short circuit test, field MMF is necessary to overcome drop across armature resistance and leakage reactance, and also to overcome the effect of armature reaction. Okay, these are the main things. Okay, next, so but drop across armature resistance and leakage reactance is very small. That's why we are neglecting these things, these drops. Okay, next, thus in short circuit test, field MMF circulates the full load current, balancing the armature reaction effect. Okay, so here in the short circuit test, field MMF circulates the full load current, that too for balancing the armature reaction effect. Okay, So the value of ampere turns required to calculate full load current to circulate full load current can be obtained from short circuit characteristics. Okay, this is denoted as FAR, F suffix AR. Okay, why? Because in this case I am taking the armature reaction effect, that is FAR. So that means we have to measure the full load current. Okay, that means I am taking ampere turns, that means FAR. So under short circuit condition, as resistance and leakage reactance of armature has no significant role. Why? Because the drop across the armature resistance and leakage reactance is very small. That's why I am neglecting those drops. So here I am telling the same point. Under short circuit condition, as resistance and leakage reactance of armature has no significant role, the armature reactance is dominating, and hence power factor of the purely reactive circuit is zero, lagging. Okay, next, hence FAR gives demagnetizing ampere turns. FAR gives demagnetizing ampere turns. So thus the field MMF is entirely used. That means the field MMF is entirely used to overcome the armature reaction, which is wholly demagnetizing in nature. Which is wholly demagnetizing in nature. And next, the two components of total field MMF, which are F0 and FAR, are indicated in OCC curve, that is open circuit characteristics, and SCC curve as shown in the below. So this is the characteristic diagram for the MMF method in for the both cases, open circuit and short circuit test. So here the open circuit characteristic is drawn between open circuit voltage and field current, and the short circuit curve is drawn between the field current and short circuit current. Okay, so here F naught gives the open circuit characteristics, and FAR gives the full load short circuit current. This is indicating the rated terminal voltage, that is F naught, full load short circuit current, that is FAR. Okay, next, so if the alternator is supplying full load, okay, if the alternator is supplying full load, then total field MMF is the vector sum of its two components, that is F naught and FAR. Okay, so this depends on the power factor of the load which alternator is supplying. Okay, this depends on the power factor of the load which alternator is supplying. So the resultant field MMF is denoted as F suffix R. Okay, let us consider the various power factors and the resultant FR. So to prove that different power factor conditions, I am taking the various power factor loads, that is lagging power factor, leading power factor, like that. So here I am taking firstly zero lagging power factor, zero lagging power factor. So as long as the power factor is zero lagging, the armature reaction is completely demagnetizing. Okay, so for that one I am taking the below diagram. So here I am taking 3 points, that is OAB. So firstly we are taking OA. So it consists of F naught, that is the open circuit MMF, and AB, that is short circuit MMF. Okay, so here as long as the power factor is zero lagging, the armature reaction is completely demagnetizing. Hence the resultant FR is the algebraic sum of the two components, that is F naught and FAR. So in the field MMF method is not only required to produce rated terminal voltage, but also required to overcome completely demagnetizing armature reaction effect. So that is shown in the below figure. So this is the diagrammatic representation of that point. Okay, so OA, so this gives the rated terminal voltage, and AB, this gives the demagnetizing armature reaction effect. Okay, FAR. Next, zero lagging power factor. Okay, so for the continuation of this one, as long as the power factor is zero lagging, the armature reaction is completely demagnetizing. Okay, hence the resultant FR is the algebraic sum of the two components, that is F naught and FAR. Okay, so field MMF method is not only required to produce the terminal voltage, but also required to work on the completely demagnetizing reaction effect. So from this diagram I am taking, we are having OA and AB. So OA gives the F naught and AB gives the FAR. So here OA is equal to F naught. Okay, and AB is equal to FAR. So here it is completely overcome the demagnetizing armature reaction effect. Taking totally OB is equal to FR, that is the resultant MMF. So OB is equal to FR, that is equal to combination of F naught and FAR. So here the total field MMF is greater than F naught. Total field MMF, that is FR, is greater than F naught. Okay. Next we have zero leading power factor. So up to now we discussed about zero lagging power factor, and now I am coming to discuss zero leading power factor. So here when the power factor is zero leading, then the armature reaction is totally magnetizing and helps main flux to induce rated terminal voltage. Okay, hence net field required, that is FR, is required, field required is less than that required to induce the rated terminal voltage normally. So as part of this function is done by magnetizing armature reaction component. So previously for the zero lagging power factor, I am taking demagnetizing. Okay, demagnetizing armature reaction component. So here I am taking magnetizing armature reaction component for the zero leading power factor. So here the net field MMF in this MMF method is the algebraic difference. So actually in the previous case I am taking algebraic sum of the two components, that is F naught and FAR, and for the zero leading power factor now I am taking the algebraic difference between the two components, that is F naught and FAR. That means FR is equal to F naught minus FAR. Okay, so this is the diagrammatic representation for that explanation. So here also I am taking 3 points, that is OA and OB. Sorry, OA and AB. So here OA is equal to F naught total. Okay, and next AB is equal to FAR. Okay, here I am taking the magnetizing. So magnetizing effect, that is OB is equal to F naught minus FAR. This is the algebraic difference between F naught and FAR. So that is equal to FR. That is the resultant field MMF. So here the total field MMF is less than F naught. That is FR is less than F naught. In the previous case we have FR is greater than F naught. Okay. So this is for zero leading power factor. And next coming to the unity power factor. So under unity power factor condition, the armature reaction is cross magnetizing and its effect is to distort the main flux. So for the zero lagging power factor, I am taking demagnetizing effect, and for the zero leading power factor, I am taking the completely magnetizing effect. And next I am taking for the unity power factor, that is cross magnetizing effect. So thus F naught and FAR are at right angles to each other, and hence resultant MMF is the vector sum of F naught and FAR. So in this MMF method, so this is shown in the below figure. So here also I am taking one diagram to represent the unity power factor load of an alternator. So this one. So here F naught and FR is the FAR is right angles to each other. So here I am also taking 3 points, that is OAB. So here OA is equal to F naught, that is for the open circuit, and AB is equal to FAR, that is for the short circuit test. So here I am taking the cross magnetizing. That means from this diagram OB is equal to FR is equal to F naught plus FAR. F naught plus FAR. This is the vector sum, not algebraic sum. It is the vector sum. Okay, that is Fr is equal to F naught plus FAR. So here below is the following consideration for MF. So this is for the different power factors of the alternator, and next I am taking some considerations for MMF method to determine the voltage regulation of alternators. Okay, voltage regulation of alternators. I am taking some considerations for the MMF method. So see those considerations. Firstly, I am taking the general case. That means now consider that the load power factor is cos phi. Okay, so in such case the resultant MMF is to be determined by vector addition of F naught and FAR. Vector addition of F naught and FAR. Okay, so if you take the cos phi is lagging power factor, so here when the load power factor is cos phi lagging, the phase current, that is IA phase, lags the V phase by angle alpha, angle phi. Okay, next the component F naught is at right angles to V phase. Okay, while FAR is in phase with the current IA phase. Okay, So this is because the armature current IA phase decides the armature reaction. Okay, the armature reaction FAR due to current IA phase is to be overcome by the field MMF. Okay, this is the general case. Okay, and next I am taking, so hence while finding resultant field MMF, okay, while finding resultant field MMF, okay, that is FR. Here minus FAR, that is the negative sign of FAR, should be added to F naught vectorically. So if you see this diagram, you will understand. So this is because the resultant field MMF tries to counterbalance armature reaction to produce rated terminal voltage. That's why here minus FAR should be added to F naught vectorically. Okay. So the phasor diagram of ampere turns method or MMF method is shown below. So here I am taking in the diagram, phasor diagram. Okay. So here I am taking the V phase and IA phase. So this is for the MMF method phasor diagram. So here the V phase is right angles to the E naught phase, that is the no load voltage at 90 degrees, that is the right angles, and the angle difference between the phase difference between V phase and IA phase, that is phi. Okay, and next we will have the resultant field MMF, that is FR. So here for the FR I am taking the, I am adding the minus FAR to the F naught, minus FAR to the F naught vectorically. Okay, so here we will have the terms FAR sin phi and FAR cos phi. So here also I am taking the 3 points, that is O A B C, that is for O A B C. So by using these we have to determine the voltage regulation. Okay, so here, so from the phasor diagram, the various magnitudes are, so from this diagram, OA is equal to OA is equal to F naught. Okay, and next AB is equal to FAR. So AB is equal to FAR. Okay, and next OB is equal to FR. That is the resultant field MMF. Okay, so consider the triangle, that is OCB. So if you observe the phasor diagram, we have the triangle, that is OCB, that is the complete triangle. Okay, so from the triangle OCB, which is right angle triangle, so the FAR is split into two parts. So if you observe the diagram, the FAR is split into two parts. One is AC, that is FAR sin phi, and BC, that is FAR cos phi. If you observe the diagram, you will understand. So the FAR is split into two parts, that is AC is equal to FAR sin phi and CB is equal to FAR cos phi. Okay, so from that when I am writing FR is equal to F naught plus FAR sin phi whole square plus FAR cos phi whole square. So here FR can be obtained from the above relation. Okay, so that is cos phi leading power factor. Next one is cos phi leading power factor. So here when the load power factor is cos phi leading, the phase current, that is IA phase, leads the V phase by angle phi. So IA phase leads the V phase by angle phi. So the component F naught is at right angles to V phase and FAR is in phase with IA phase. So if you observe the diagram, you will understand. So the resultant FR can be obtained by adding FA to F naught. The phasor diagram is shown in the below figure. So this is the phasor diagram for the leading power factor. Okay. So here the IA phase, that is the phase current, leads the V phase by angle phi, and the component F naught is right angles to the V phase, right angles to the V phase, and FAR is in phase with IA phase. Okay, FAR is in phase with IA phase for the leading power factor. Okay, next, so from the phasor diagram, various magnitudes are, so similar to the previous, that is the cos phi lagging power factor. So here also I am taking the magnitude, various magnitudes, that is AC is equal to FAR sin phi. If you observe the diagram, you will understand. AC is equal to, this is AC is equal to FAR sin phi. Okay, and next we have BC, that is FAR cos phi. BC. So this is FAR cos phi. Next, OA is equal to F naught. If you observe the diagram, you will understand OA is equal to this is OA is equal to F naught. Okay. Next, AB is equal to FAR. AB is equal to FAR. From this diagram, AB is equal to FAR. Okay. AB is equal to FAR. And next we have OB is equal to FR. That is the resultant MMF. OB is equal to FR. Okay. Next, so consider the triangle OCB, which is right angle triangle. So compared to that one lagging power factor cos phi, here also I am taking the triangle OCB, which is right angle triangle OCB. Okay. Next, from that right angle triangle, from the Pythagoras theorem, you know the formula OB whole square is equal to OC whole square plus BC whole square from the OCB triangle. Okay, OB whole square is equal to OC whole square plus BC whole square. So you already know OB is equal to FR. Substitute here. So in the OB place, I am substituting FR. So that means FR whole square is equal to, you know, OC, that is F naught minus FAR sin phi whole square plus BC, you know, FAR cos phi. So this is the resultant MMF for the leading power factor. So from that relation we have this characteristic diagram, open circuitation, short circuitation. So you already know the characteristic diagram drawn between for the open circuit test, that is no load voltage versus field current, and next short circuit characteristic is drawn between short circuit current versus field current. So here this is the characteristic diagram. So here we have F naught for the open circuit test and FAR for the short circuit test and FR for the total resultant MMF. Okay. Next, so by using those relations, that is open circuitation, short circuit test, resultant field MMF FR for any power factor load condition can be obtained from the above MMF method characteristic diagram. Okay. So once FR is known, that means resultant MMF is known, obtain a corresponding voltage. Okay, which induced EMF, that is E phase. Okay, required to get the rated terminal voltage V phase. Okay, this is possible from open circuit characteristics. Okay, so once E phase is known, then the voltage regulation can be obtained. That is the formula, that is the percentage of voltage regulation is equal to E phase, that is the no load voltage, minus V phase is the full load voltage, that is E phase minus V phase by V phase into 100. Okay, so this is the explanation for the MMF method of an alternator. Okay, so in the next class I am going to discuss another method of indirect method, that is ZPF method. Okay, I am going to discuss that one in the next class. Okay, thank you.